Ka tangi te titi, ka tangi te kāka, ka tangi hoki a hau, te he mauri ora. E na mana e na reo o rakatira mā tēnā koutou katoa. Tēnei kātou te raro o te maru o ka mana whenua, ka te mamo e waitaha kaita, tahu no mai haramai, welcome. Ki te whare tūnei, tēnā koe, tūtonu, e mā te haere hoki atu rā ki te pō. Ko waiao, no Otapoti ahau, ko Katarani te iwi, ko o tāka whakaihu waka, ko Richard Blakey ahau. Hi everyone, I'm Richard Blakey. I'm Deputy Vice-Chancellor Research and Enterprise. It's my great privilege and pleasure to host you tonight for this inaugural professorial lecture where we celebrate the achievements of Andrew Gorman, Professor Andrew Gorman, in achieving the highest academic standing at our university. These events are a celebration and I'm here to welcome you, say a few things, and hand over to Professor Richard Barker, Pro Vice-Chancellor, Division of Sciences, with a more formal welcome. It's our great pleasure to invite you all here tonight and to those online or watching from the future to this event. And in particular, your wife Sandy and daughters Claire and Maggie are here with us tonight. Kia ora koutou. And I believe that online or in the future, Connor, your son, and your parents, John or Eileen, are watching and will watch this on rerun, and I'm sure this is going to be a fantastic event. We have set very high standards for our professorial appointments and promotions at the University of Otago. We use international referees to quality assure those processes, but quite very simply, we require outstanding leadership over a sustained point of time in the main areas of academic endeavour in research and teaching and service, and we're going to hear some of that tonight. Andrew works on big issues of global importance. It is big science that he does with big collaborations, supporting work on the land, in the ocean and on the ice, and from a country that we don't classify ourselves as being big, but the work that Andrew does in mapping seafloors and land and Arctic and Antarctic ice sheets, we've got to remind ourselves that our responsibility for this planet is quite significant. Our responsibility to cover about 25 million square kilometres of ocean and seafloor. Andrew's work has been responsible for taking a look at some little bits and pieces of that, and that represents about 5% of the planet. So it's big work that needs people with big ambitions and working together as large teams. Andrew has done that in the role of an academic, teaching and supervising graduate research students. Many students have come through his supervision that have now gone on to significant roles both in academia and in industry. The kinds of support that we expect from our high-level academics, encouraging people into their future career paths. It's also notable that whilst Andrew has big ambitions and big research on a global scale, he has been a very good servant both of the university and service as a head of department, but of our local communities as well. And one thing that struck me was local service that Andrew has done. My father was an academic and would also be the kind of person that would, if someone picked up the phone and wanted them to work on a local project, wouldn't say, I'm too busy, that's not big enough for me. So your work with some of the local groups trying to find buried armaments in some of our parks and reserves was one that struck me as being particularly notable as the kind of service that we expect from an Otago academic at the highest level. So please, on behalf of the university, can we all join in congratulating Andrew on this well-deserved promotion to professorship as I invite Professor Richard Barker to give a more formal welcome and introduction. Thank you very much.
Professor Blakey, tēnā koe. Professor Gorman, tēnā koe. Professor Sterling, tēnā koe. Deputy Vice-Chancellor, tēnā koe. Friends and colleagues, tēnā koutou, tēnā koutou, tēnā koutou katoa. It is my great pleasure tonight to introduce our speaker, Professor Andrew Gorman, from the Department of Geology to give his inaugural professorial lecture. As indicated by Professor Blakey, Andrew was promoted to Professor in February of this year, and tonight we get to celebrate this significant achievement. Andrew was born in Carrickfergus, to me a place familiar through the beautiful folk song of the same name. The version I'm familiar with was sung by Van Morrison and the Chieftains. Those with a better geographical knowledge than me can tell you that Carrickfergus is an ancient town in Northern Ireland known for many things. Just one, it was the last mooring place for the Titanic before she set off on her one and only journey across the Atlantic. Conducting a much safer passage across the Atlantic was a young Professor Gorman, dragged, I'm using his words, by his parents across the ditch to set up life in Canada, in the small prairie town of Mossbank, just south of the delightfully named metropolis of Moose Jaw in Saskatchewan. The next move took the Gormans to the northern frontier town of Yellowknife, a place that lives and breathes geology. Like Dunedin, it was founded on gold mining, and unlike Dunedin, it is now the centre of a thriving diamond industry. Here, Andrew developed an interest in geology, and the foundation was laid for an academic scholarship to the University of Calgary and a place on the university swim team. He was known as one of the rocks for jocks. And here, Andrew met Sandy, a trainer for the University of Calgary swim team, and I suspect still training Andrew to this very day. A science bachelor's in geology from Calgary led to a full-time position with Chevron in Calgary in 1987, which sparked his interest in research, and it also provided enough disposable income for, among other things, a 6-week cycling trip around New Zealand. But drawn to academia, Andrew headed off to graduate school at the University of British Columbia in Vancouver, where he completed his PhD in 2000, followed by a postdoc at the University of Wyoming in Laramie. In April 2002, Andrew was flown to Dunedin for a 3-day job interview here at the University of Otago, and this was successful for all parties. And Andrew started at the University of Otago in January 2003 as a lecturer. So tonight we celebrate his progression fully through the academic ranks. As we have heard from Professor Blakey, promotion to full professor at the University of Otago is far from easy. You must excel in all 3 academic domains of teaching, research and service, and Professor Gorman has truly excelled. As we have heard, Andrew's research primarily involves the application of seismic imaging techniques to investigate geological and oceanographic problems. He is productive and has published 1 book, the intriguingly titled Māori and Mining, as well as 3 book chapters and 54 journal articles. With his seismic work, which has been on land and ice in Antarctica and on water using our research vessel, the Polaris, Andrew's research is truly cross-disciplinary, and his projects contribute to research across the university in departments such as marine science, mathematics and statistics, surveying, and of course, geology. His geophysical research necessarily consumes significant amounts of time collecting field data, whether in Antarctica or on board the Polaris, or laying out instrumental arrays across paddocks in Westland, or in fact in our botanical gardens. Field trips are expensive, and Professor Gorman has been very successful in attracting significant amount of research funding to support this, including 2 Marsden research grants and 3 MBIE program subcontracts. One of the standout features of his publications is that his postgraduate students are central to almost all of his research, and his research is also central to his teaching, and in particular field-based teaching. This includes students being taken on the RV Polaris, students being taken to the North Island on enhanced field excursions, recently made possible by a generous donation from Clint and Jan Nauman. Locally to the Abbotsford landslide, a reminder of the fact that our landscapes are dynamic and pose significant hazards. A local field school to Warrington Beach, and one a little further afield to Rakiura, Stewart Island. Incorporating his research into his teaching has been instrumental in fostering talent, and many of Andrew's students have gone on to successful research careers. The final domain of academic performance that requires excellence is service to our academic and professional communities. Professor Gorman has played a leadership role on the national executive committees of the New Zealand Geophysics Society, the Geosciences Society of New Zealand, including positions as president and past president. He is also on the editorial board for several journals, including as editor of the International Journal of Pure and Applied Geophysics. My final comments are on his university service. Professor Gorman has been a member of many university committees and working groups for a long period of time, and this includes important committees such as the University Research Committee, Physical Sciences Panel. But for me personally, it's his service as Head of Department of Geology that stands out. As we all know, he's especially cheerful and optimistic, despite having to have worked on some really confronting challenges over the last couple of years. And it's always with the welfare of his staff in mind. And so I want to say thank you, Andrew, for that. But I think you've heard enough from me. It is now time to hear from Professor Gorman himself. Please join me in welcoming Professor Andrew Gorman.
Right, kia ora. Kanaka te manga, ko Saskatchewan te awa, ko te aherihi toku iwi. Ko no Canada aho. Ko Gorman toku ingawa whanau, ko John Rawa, ko Eileen Oku Matawa, ko Andrew toku ingawa. Kia ora. I think that starting off a talk with a pepeha like that is really appropriate for, particularly for people in the earth sciences, and even more so ones who work on the ocean, because the Maori tradition of having a mountain and a river is something that speaks very, very closely to most of us in the earth sciences. The view that you can see right here is from the Nocha, which is on Belfast Lough. So just down and to the left is the town of Carrickfergus that Richard was talking about that I was born in. Belfast is down to the right, and you can imagine the Titanic right there in the picture down below there. But that's not, I didn't pick that as my water body. I picked the Saskatchewan as my river because when I was 4 years old, my parents brought me to Western Canada. I spent almost half my life living within the catchment of the Saskatchewan, which you can see in the picture here, rises in the Rockies and comes through most of the provinces of Alberta and Saskatchewan into Manitoba, and then flows out eventually through the Nelson River into Hudson Bay. And so Saskatchewan, if you are fans of the Proclaimers, you can play that back later, and you can practice how you say that with cap in hand. I gave Richard the instructions so he could look at that anyway. But the title of my talk was basically making a bang, and I was trying to think of things that link together the areas of my work, and I think blowing things up is basically part of what I've done for a good part of my career, and so I think that's where I'm going to try to make the theme for at least part of this talk. I'll start off talking a little bit about what it is I actually do in terms of making those bangs. Then I'll revisit a little bit about how I got there, and then I'm going to try to bring things back into a little summary of probably 5 favorite seismic sections, which is what the bangs end up making, that answer some questions about the world, and we'll see where that goes from there. So most of you know that I like to get on planes and fly somewhere. This is for Phil, who's in the audience. He wanted to see planes, so I've got planes. And flying south to Antarctica, get a great view from these big American cargo jets, the C-17s. Landing on the ice. But then what happens when I get there? I guess usually bringing students and colleagues in tow with me as well. Others know that I don't always go to Antarctica. Sometimes I get in a helicopter, and if I'm lucky, and somebody's paying the bill, and fly into Fiordland, or more often it's getting on a ferry and going across Lake Manipuri. But getting out to the Polaris and putting some gear in the water that also makes bangs, and collecting seismic data, again, usually with lots of students and colleagues. So I'm going to show you a little bit about what I do when I actually get there. And dynamite or explosives plays sort of a central role. Making a bang it's one of the ways that have made the bang, probably the more dramatic way. These are the boxes of of explosive cord that we had in Antarctica last season that we only blew up about half of it actually, so we can go back and do some more. Coming from some pretty exotic places and with warnings that are sometimes not even in English, and then putting together things that look like this and shoving them down holes and blowing them up. So I'm just in case you're worried, I do have the qualifications from New Zealand anyway to do that, and it doesn't really look like this. So that's not what we're going to see. Anyways, so I thought that I'd start off by showing you a little video of a little bit about what some of our sources look like, and there's a couple of students in the audience who will recognize themselves from here. So I'm going to start off with some of the shots, some of the explosions that we made from just this last season when I was down at Discovery Deep south of Scott Base.
Here's the end of the trigger wire.
You can hear this.
With the wires crossed. Waiting for Hamish up there to finish his wiring up job. And when he's finished, he'll walk away to a safe distance. And we'll be able to take our wire and plug it into the dog box. And Charlotte can make it go boom. So Charlotte has it wired in. She's signaling that it's time to make the sound.
There you go, and that's what happens. And we do that another 500 million times over the next few days. I put in a few more examples because they are kind of fun. You never really get tired of them. So this season, these are all of our shots look like this season.
By far the hardest job
the downside is that when you're doing a survey like this, you'll see in a second that the last survey we had last year was quite easy for putting in sources.
Along our line.
This was a bit more complicated because we had to dig geophones, these things,
Jenny almost into the bottom of a hole.
The ground. We can pass this
Planting
around.
the geophone in the hole,
Props.
arm's length deep,
There you go.
and connecting it to the takeout cable that you can see right here. If I was being nice, I'd actually be doing this for her. But since I'm videoing, I'm going to let her do it herself.
Jenny's a colleague of mine from GNS Science up in Wellington.
And Jenny's making it look easier than it really is. Sometimes these are a pain in the ass to connect.
So these are essentially the listening
line.
devices that are going to record the vibrations, the sounds that we're generating.
I am armed and ready for your shot, Bruce.
Here it comes.
And that was it. So you can imagine that Oben, I don't know if Oben's here somewhere, he had a much more exciting time than Will did because Oben's survey was the one that blew up 600 times. Will just got to hear little thuds, and only about 60 of them over the course of his season. But the data in both cases were pretty nice. In the case of the streamer survey that I was involved with last year with Oben, we were using a streamer from Alfred Wegener Institute in Germany. This is it in its case, and you can see that basically it's a system that you can tow behind a skidoo. So you didn't have to bury the geophones in. These are the little geophones that Charlotte's wiring up here. In this case, they're just in little cylinders, and they have gimbals, and so they just drag behind the skidoo, and they're much easier. So we were able to collect a lot more of them. And this is what the det cord looked like that you were seeing just blowing up. So we had a 10-meter section of this, which we then wired up and detonated. Came back to the dog box, and you can see that one of the little detonations is happening there in the background. So just in comparison, the survey that we had last year at Discovery Deep, we ended up having 576 shots over 18 days. So we were getting really productive by the end and actually got pulled out a little bit early. We have about 600 more shots ready to go for the next time we get funding to go down there, hopefully in not this summer, but the summer after. And then a typical survey similar to the one that Will would have been involved with would have had much fewer shots that were much more spaced apart. But the quality of the shots, because they're buried in and frozen into the ice, is usually a lot higher. So with the 60 shots, it still took about twice as long to collect data of the same, roughly the same quality, and with actually a lot more work. So we're going to try to stick with the snow streamer behind the Skidoo method in the near future. So that sort of leads to what actually gets recorded by the computer. And it turns out that what we're measuring is waves, but not waves like this. Is Maggie here? That's it. Oh, there she is there. So my daughter Maggie, and actually Leilani, you're in this picture as well. So I'm just seeing who's here in the audience. So if you look right here, this boat, I want you to keep your eyes on this little video that's happening now, because this is Maggie and Leilani at the New Zealand Surf Life-Saving Nationals that were held the year before this in Christchurch. And anybody else who was there, including me, might have a little case of post-traumatic stress disorder by watching this video, because it was one of the scariest competitions I've ever been involved with. So I'm going to turn the sound off for this, make it a little bit easier. It was beautiful weather, but this happened the week after the cyclone came through. And the reason I'm showing you this is because waves is what we think of when we think of sound flowing through the earth. On a surface like this, we're looking at surface waves, which are a little bit different than what we're thinking about traveling out through the earth. But you can imagine each wave is going to have some sort of an amplitude, like this one, around 3 meters. And you can see the boats, which are making no progress at all getting out through the waves. They're basically bobbing up and down as the waves come past. And so you can think about a wavelength, a distance that's happening between the crests of these waves of around 70 meters. And then as each wave comes past, you're basically bobbing up and down in place. So you'd think of this as basically a temporal wave. Now the boat that did make it out through the waves, you can see it coming through here. This was not a team from Warrington. We don't want to know where they're from. They basically are showing the temporal part of this wave. So in 13 seconds, that 70 meters of wavelength equates to how far that boat can travel when it's sitting on that crest. People who are into surfing would understand this as well. So you have both this temporal and spatial aspect to waves. Now, when we're thinking about this in traveling out through the earth, we can think of those waves traveling out in all directions. I'm generating waves right now by speaking to you that are traveling out in all directions in this room. A compressional wave is similar to that as what we actually try to image when we're sending that sound down into the earth. And equation for Boris and for Andrew. Okay, you wanted an equation, didn't you, Andrew? So I've got one equation here, which is my favorite equation. This is the wave equation, and it's a differential equation that's basically relating the second spatial derivative of displacement to the second temporal derivative of displacement. And by understanding how those things relate to each other, you can then predict how sound is going to travel out through different media. So that's basically what we're thinking about when we're looking at seismic waves traveling through the earth. Now, bringing this back to the marine example, I could have done this with ice as well, but here's the Polaris for scale up at the top. You can see this little dotted yellow line that's going across on the ocean surface. And I put this together quite a few years ago when I was on a cruise and had too much time to play with animations in PowerPoint. But you can imagine the sound coming off the back, following these rays, where it's reflecting down back off the seafloor, and then coming back up to the sea surface and being recorded by hydrophones, which are being towed behind the boat. So similar to the geophone that's passing around in the room here, except one that senses pressure within the water. So it's basically the same technique. You can also get sound waves that travel down through the seafloor, reflect off any sort of geological contact in the subsurface, and then come back up to the surface and are recorded as well. So as the boat's going along, it'll have repeated booms that'll be going off the back, or if you're in Antarctica, it could be these individual shots that are being fired, then being recorded by the surface recorders. All that stuff gets shoved into a computer, and I'll skip over all the fun part, which a lot of my students spend a lot more time than in the field sitting in front of a computer dealing with, and you end up getting a picture of something like this. So this is there might be some people here in the audience who I could test to see if they know where this is or what this is, but one of the things that a seismic section is no good about is it's no good unless you have scales on it. So you have to think about what am I actually looking at right here. And so it turns out that the horizontal scale in this image is about 50 kilometers. So this was taken by a boat, and I'll spoil the surprise by telling you it's just offshore from Otago. So we're going from close to Dunedin here on the left-hand side, going out about 50 kilometers offshore, and then stopping. And then the vertical scale on here, because we're looking at echoes that are coming back from the subsurface, is in time. So we're listening for the time it takes for sound to travel from the surface down to whatever reflecting body there is and back up to the surface again. And so one of the things that we really want in geology is we want to be able to know how deep something is, how deep is the ocean, how deep are these different units below the seafloor. And so to do that, we need to know how fast sound travels through the water or through the rock that we're looking at. And so that's something that we spend a lot of time trying to analyze in the data as well. But the main thing you can see here is you're seeing down to the seafloor. It's a pretty rugged seafloor here in this case. This 2.5 seconds that you can see here would correspond to somewhere around maybe 2.5 kilometers of depth, depending on the velocities. And so we're looking at water depths here that are over a kilometer deep. At that point. And these really deep chasms that you can see and that are incised into the seafloor are the Otago Canyon system that are just offshore. So this is the Karitani Canyon closest, and then heading towards sort of obliquely across the shore, heading north. We can also see geological contacts in the subsurface. And one of the things I've spent a bit of time, including one of the Martians I've been involved with, doing is trying to get reflections back from oceanographic contacts. So this oceanographic contact that there is probably the boundary between subtropical and subantarctic waters. So it is, we are bathed in subtropical waters, believe it or not, here in Dunedin. All right, so that's basically what a seismic section is looking like. The sound, the strength of the sound that comes back is going to be reflected in the color that you can see on this pattern. So this is actually a whole load of little sound waves that are smashed side by side over 50 kilometers. If you zoomed in on that, you'd be able to see individual traces coming down through there. Where the echo coming back is strong, you end up getting dark colors that are blue and red in this case. They could be whatever color code you want to make them. But that's essentially what a seismic section looks like. All right, so I'm going to revisit a little bit of the story that Richard told about how it all came to this in my next little section, so you can sort of get a bit of a feel for why I ended up becoming a geophysicist. As Richard, I'm not going to do it all, but and perhaps somebody who works in cold places as well. So this is a picture of me, believe it or not, back when I was about 6 years old, living in Mossbank in southern Saskatchewan. So it looks a little bit like Canterbury, except it's flatter and the roads are straighter. So it's it's not really the most inspiring place to get into geology, but maybe geophysics. If I lived there a little bit longer, it's good for seeing through. But we ended up moving to a much more interesting geological place. Still pretty flat because it's been eroded away by glaciers. But this is Yellowknife in the Northwest Territories, which is either really, really old exposed rock, or else where the glaciers have carved down, you get these shallow lakes. And you can see one of the big gold mines here in the corner with the little red roof on the top. That's the Con mine. And it looks nice in the summertime. In the winter, this is what Yellowknife looks like. It's also a bit like what Prince Albert looks like and what Calgary looks like in the winter as well. So I spent a lot of time in places that were quite snowy and frozen. Richard also alluded to the fact that I was on the swim team. I probably shouldn't linger too long in this picture, but see if you can find me. And then this one even worse. So I went back trying to look for some old pictures. And you might even see Sandy in this picture. This may be the first picture I have of Sandy. I was trying to find that when I think I'm 18 in this picture. And Sandy is too. And it's also where I really got into geophysics. So at the same time I was on the swim team at the University of Calgary, I was also at a pretty good geophysics program there as well. This is a picture from the field school, the geophysics field school at the University of Calgary, and we did a lot of getting out and trying different techniques, which I've tried to really duplicate here at Otago as well. And we'll be having our field school again at Warrington Beach next month. So we'll be back doing a lot of these same techniques with students this year as well. When I finished at university, I think it was sort of that combination of practical experience and actually being a teamwork that I've done with the swimming that got me the job at Chevron, and it really was like the University of Chevron. I had a really great group of fellow geophysicists who had all started together. We had a lot of training projects that we were sent on. For those of you who don't know about Chevron, it's the fifth largest energy company in the world. It sells petrol, and it used to sell petrol in New Zealand until they sold the Caltex stations away. But it's basically the parent company of Caltex. And it's also where I really got into sort of observing geology and the water, I guess, too, in the wild, but learning a little bit about field methods. So this is a Vibra-size crew that I worked on for a year while I was at Chevron, looking a little bit dated now. Back this would have been in the late 1980s, and I was involved mostly in looking for oil and gas in Western Canada, and so I did that for 6 years, and then basically got lured away by academia, and I guess that's what hooked me after that. I moved over the Rockies to Vancouver, and instead of going, you think by this picture maybe I'm going to become a marine geophysicist now, but instead of that I actually started looking at the geology of the central part of North America, the Craton, and started blowing things up. So this was the start of blowing things up. So this is one of the shots from the Deep Probe project, which ran from northern Canada down into the southern states. So almost 3,000 kilometer long profile. I never actually saw any of the shots go off, which is quite sad because they all happened at night. We were doing them when they weren't going to bother anybody, and there wouldn't be any traffic on the ground because we wanted to record the vibrations a long way away as well as possible. And this is the one shot I did get to after it had gone. This was actually only a 5,000 kilogram explosive charge. So it was 5 holes, each 100 meters deep, with the bottom half of the hole cased and filled with explosives, and then detonated. And so you can see that one of the pipes, the casings didn't quite get the whole way out. The other one came out and landed here. I wouldn't have wanted to be too close to that. The shots were all done either in quarries or places where you could blow things up easily, and they were done by professionals as well. So meanwhile, the rest of us spent our time wandering around in fields, scantily dressed, and digging holes. I seem to like digging holes as well, or having my students do it, and burying seismometers. So here's a 3-component seismometer being buried in Colorado as part of that Deep Probe experiment. And I'll show you some of the data from that here shortly. After my PhD, though, I ended up going to Wyoming, and that's where I really got into marine science. My first voyage was on the Ewing, leaving here from Newark, New Jersey, and heading out to the Bermuda Triangle, where we spent two months trying to find gas hydrates in the subsurface. And we were using basically an air gun source behind the Ewing, and recording it with an 8-kilometer long hydrophone array, which is what you can see here coming off the spool and being deployed off the back of the boat. We also had ocean bottom seismometers, which we could drop down to the seafloor and record the vibrations the same way as you would if you were burying a geophone in the ground, except this one's sitting on the seafloor, maybe 2 or 3 kilometers down into the subsurface. But then Aotearoa beckoned. We arrived here with our kids looking much smaller than they are now, but we're still in Warrington, so we haven't moved too far. Here's with Alan and Robin. I'm not sure if they're here tonight, who welcomed us when we arrived, and Gary and Kate Wilson as well. So they've been around since the beginning. Lots of others as well, I must say. And it's also where I really got my start into collecting some high-frequency marine seismic data, which we've done. You can see, if those of you who've been on the Polaris recently, you can see that the equipment has definitely improved. The plotter you can see there on the left is not something I would really wish on anybody. If you think the Polaris is seasick, it makes you seasick, you should see what the Munida did to you. So that I haven't had to think about that since 2007. And Mike Trinder is there on the right there as well. All right, so that sort of gets us here to New Zealand. And so what have I been doing? So I've got about this next part could go on for hours, but I've limited myself to 5 slides, which have many little clicks on them, and they each are around one seismic section. So going back to my days in my PhD project, that's really where I got my start looking at some of these big questions about how have the crust and the lithosphere evolved. So for those of you who aren't earth scientists, I'm looking at the layers of the Earth. The outer layer of the Earth is sometimes you know it as the crust. The lithosphere is involved with plate tectonics, and our goal with the Deep Probe project, which is part of Lithoprobe, was to look down as deep as we could with controlled source seismology. So all through the 20th century, a lot of information had come, a lot of knowledge had come about our makeup of the Earth by using earthquakes as sources. But I'll leave that to Mark and others who like earthquakes. Maybe have, I don't know if Donna's here, but there's a few people in Dunedin who do use earthquakes as seismic sources. But here we are trying to use control sources. And the main reason why you use control source, blowing up your own dynamite, is that you can really tell when the earthquake or when the sound happened. And so if you don't know that precisely, then making an image is quite a challenge. And so we have, this is just one of our shots that happened in northern Alberta. And I've got 3 different colors here which correspond to sound that's traveling along different rays. The red ones are rays that are traveling through the crust, so they go down and they curve and come back up again as the velocities get faster. The light blue ones you can see here are rays that are traveling down and reflecting off the boundary between the crust and the mantle, which is called the moho. And then the light green ones are ones that are traveling down and traveling through the upper part of the mantle. And these are ones that haven't been recorded much by control source methods before, mostly because they're traveling so far. You can see that the horizontal distance on here is in kilometers. So from the distance where the shot was here, this would have been one of the ones similar to the one I showed the picture of there with 5,000 kilograms. We're looking 1,200 kilometers away. So this would be like setting off a shot here and recording it in Northland. So it's a long way away. And it means that we could see down maybe as much as 120, 130 kilometers into the Earth, into the upper mantle. And the reason for doing that was trying to understand the makeup of, in this case, North America, continental makeup. In New Zealand, Nick has just been lecturing on some of the interesting continental crust that we have in New Zealand, but here the crust is a lot older. So these red blocks are Archean crust, which is getting up over several billion years old, and most of the core of North America is made up of this Archean or slightly younger, over a billion-year-old Proterozoic crust. And so it was these blocks of really, really ancient continental pieces that we were trying to image with the Deep Probe experiment. And so I'll skip over some of the data, but this is essentially what the last model looked like. That was basically the output of my PhD, looking at the 3 main blocks that you can see here through southern Alberta and Montana going down into Wyoming. And these are old blocks that would have originally been separate continents that collided together, would have had subduction zones between them, which you can actually still see, which is pretty amazing. So these subduction zones, the blue here and the dark one here, actually have reflections that come back from them. So we know that we have something that's been preserved as a subduction zone for probably more than 2 billion years. It's pretty amazing. And then underneath Wyoming, a little bit of this Medicine Hat block, this is on the southern part of my survey, mostly on the American side, is this more recent Proterozoic underplating. So having this picture for the first time of what the structures of these blocks was like was a lot of fun to be involved with. Not only that, but on top of this, basically you have 4 kilometers of sediment, which I'm ignoring for this part. So that's where most of those wheat fields of southern Saskatchewan are located. Okay, so that's one. The second one, I'm skipping ahead now to my days when I was doing a postdoc at the University of Wyoming, and that's really where I got into marine geophysics. It's similar to the sort of data that I worked with when I was in the oil and gas industry as well. So marine seismic methods have been around probably since the 1960s. They've really been had their successes once positioning technology came along. And they've been responsible for finding a lot of the largest oil and gas fields in the world. If you look at the North Sea, North Africa, the Gulf of Mexico, Brazil, the slope of Australia, those are all owe themselves to this seismic method. And so it's a, I guess, arguably what's caused a lot of our problems today, but it's also given us a lot of information about what's in the subsurface. And so when we were out here in 2000 at the Blake Ridge in the middle of the Bermuda Triangle, we were looking at these features on the seafloor. This is a map of the seafloor using multi-beam data. And you can see there's this really strange pattern on the seafloor here, which is quite deep, more than 2,000 meters deep at this point. And this is what these look like in cross-section with the seismic sections. So we were looking at a place where there's these amazing sediment waves which are caused by basically an interaction of ocean currents in the seafloor. And below them is a really distinctive feature, this BSR, which is usually called the bottom simulating reflection. But when it was originally named, it was called the bullshit reflection because nobody believed it actually existed. But it turns out it's actually a boundary. If you look at it, you can see that there are horizons that cross it. But it's a boundary that's there because of extra gas in the sediment. So actual gas bubbles will be in these sedimentary units here, which are trapped in place by gas hydrates. And there's the Ewing again collecting that data. And this is a picture of what the gas hydrates look like if you drill down and bring them up to the surface. So mostly sediment, but in the gaps between the sediment, you find this white stuff, which is essentially an ice bonded with methane. And it turns out that it's a huge resource of methane on the planet. There's about the same amount of methane trapped up in this sort of stuff here as there is in oil and natural gas and coal reserves all around the world. So it's a huge amount, and no real easy way to produce it. There have been a few attempts to try to produce it as a fuel, but rather it's really more known now for its trying to understand its role in the climate cycle. Because as sea levels go up and down, pressures change, temperatures change, the stability of these hydrates change as well, and we don't really understand what their role is going to be as we go through anthropogenically changed conditions in the ocean, let alone glacial changes. This is what a hydrate looks like if you set it on fire, because it's basically a frozen ice. But if you burn it, the methane takes off up in the sky, and you'll get as a flame, and you'll find the water basically dissociates and comes up through your fingers. So you can hold it while it's on fire. I have never actually seen hydrates, and I've been working on them for 20 some years. So they're not very common. They only really occur, or mostly occur on the seafloor, or else in a lab, which is where that one was made. All right. Running on now to question number 3, what can we learn about active faults? So this is something that I was really happy to get involved with when I moved to New Zealand. Rick Simpson and Francesca Gazzetti took me under their wing, and sort of the first real fault I looked at was the Osler Fault in central Otago. And then I got involved with the deep fault drilling project, which was over on the west coast, with a cast of thousands there as well. And so if you look over here on this sort of rotated image of New Zealand, very similar to the one Donna loves, because north is sort of up at an angle. But we are looking at the side where at the location of Wataroa. And this is a zoom in of that region here. So you can sort of make out the Alpine Fault running diagonally across this figure like this, with the mountains on the southeast side and the flat coastal plains on the northwest side. And then the picture we have is basically in around this region of deep fault drilling project 2 well site. And over the course of many years, I can see Patrick in the audience as well. This is part of his master's. We collected all sorts of seismic data from here. This is Patrick didn't know this was going to be here, but this is from a paper that we wrote together, and along with a few other people as well, obviously, that included field school data, some master's projects, some dedicated data, all sorts of different sources. So it was a lot of fun getting over there to try to see if we could image the fault. And we were pretty successful. So these are 4 different images. You can sort of see where they're located here, where these 2 strands of the Alpine Fault come across the opening of the Wataroa Valley. And you can see the offset beds here. And it was these sort of sections that were really key in planning the position for the deep fault drilling project well site, which drilled basically down from the surface and tried to penetrate through the active strand of the Alpine Fault, so they could see what conditions were like close to the fault prior to its rupture. And that's another talk for another day. So on to number 4, and this is getting closer to what we're doing now. What can fjord sediments tell us about past climate? So I've really it's been a real privilege actually to spend time in Fiordland over the past while. We've been in, I think, almost every fjord. I'm still waiting to get into Sutherland Fjord, and made images of the fjords. So most of my time when I go out there is spent trolling the boomer gear behind the boat and making pictures like this. And the main thing, I guess, to get across here is that the sediments that are, you can see by these flat-lying lines here, they're in the fjords. This is the mouth of the fjord over here, which is opening out into the Tasman Sea. This is the part that's closest to the land. This is actually George Sound, a little bit sort of between Milford and Doubtful, for those of you who've been in that area. And so we've got a line that sort of snakes its way along through the bottom of George Sound and comes out to the open ocean over on the side. The flat-lying things you can see in here are essentially sediments that have filled in. And if you look at a typical fjord, this is Doubtful Sound. I didn't have a similar one of George. You can see that they're U-shaped valleys that would have originally been full of ice. And at the end of the last glacial period, that ice retreated and would have basically left an empty valley behind that might have had some moraine in it, but wouldn't have had much in the way of sediments. And so once the ice retreated, the interesting thing though is that the ice age was still, the last glacial was still on, and sea level was considerably lower, about 125 meters lower than it is today. So it would have been somewhere around where my arrow is on the outer side of the sill at the entrance to George Sound. And so George Sound, once the ice left, would have been left behind as a lake. So this would have been like Lake Horoko or something like that. Would have been fresh water that would have filled the lake until the sea level rose following the last glacial and flooded it. And so the really cool thing is if you look at some of these features in the lake, so if we zoom in up to the top end, you can see features that formed when this was still a lake. And so this is a little delta at the head of George Sound up here. And you can actually see the little sedimentary patterns in here that are formed by sediment coming out from the river at the end of that valley. And then you can imagine a lake being formed about 55 meters below sea level right now, where it would have been dammed by something else as well. And so this delta would have been coming out into a little lake and filling up this basin that now no longer had the ice in it. Once sea level rose and sea level came back up to where it is now, we would have had an ingression of marine water, and this would have, the whole environment would have changed. And so some of the most recent sediments that we see here are going to be marine sediments. And a big part of sort of the ongoing research project that we have here in the department is in Fiordland is looking at the nature of those sediments, looking at carbon storage, looking at all sorts of questions about how that has changed over time. And it's actually really short geological time. We're probably looking at certainly less than 20,000 years that all the sedimentation and infill has happened. And we can do the same thing in lakes as well, which is I don't know if Sean's here, but I've been having fun with him in some of the alpine lakes as well. Okay, final one is Antarctica, and I guess I had to save that for last. But what's happening below the Ross Ice Shelf? That's been a big focus for me over the past few years, and it's been a real privilege to get down there as well. Here you can see the Ross Sea. Just labeled here, and then the Ross Ice Shelf, which is in gray, and Scott Base, which is where we always end up flying to, is located at the southernmost point of the Ross Sea, the southernmost navigable part of the Ross Sea, where you can get boats to supply the bases that are there. And so the past few years, we've been at this location called Discovery Deep, which is about 150 kilometers south of Scott Base. Now, I didn't have time to flip. I probably should have, but I wanted to emphasize the fact that maps of Antarctica are a little bit dangerous because which way is north? And this map, every way is north. And this map, it's north is definitely up, and it's pointing at, but it's totally in the opposite orientation to what the map is on the left. So because we're south. We're below the South Pole on this picture, so you have to flip the map around. So here, so Scott Base is just off the top of this map here. So we had to fly south over Minna Bluff and got down to our research area, which is indicated here in pink. And so I've been there for a couple of years. This is some of the data that we collected as part of Will's project. So you can see we're imaging down through the ice, through the water. You get lots of reverberations from inside the floating ice shelf. So the ice here is about 500 meters thick. The water almost a kilometer thick, and then we get down into the sediments, which is what we're really interested in looking at. When we went back last year for our streamer survey, we ended up making even nicer sections, which these are my favorite ones that I've made so far from Antarctica. You can see that we're seeing faults. We have dipping strata in the subsurface. What we're not seeing is a lot of really recent sediment, which is one of the things that we're really looking for because that's part of the story for why we want to look here, is we want to see what recent sediment that's underneath the ice has looked like, so it can give us some information on past climate change. So this is showing probably an eroded part of the seafloor below the Discovery Deep area that we were in before, that's carving down through some of these older flat-lying sediments, or roughly flat-lying sediments you can see here. And hopefully someday in the future, we'll go back here with drilling equipment. This is my colleague Davin Dunbar from Victoria, University of Wellington, over on the Cam Ice Stream, where we have drilled, and they'll be drilling again this summer. So you'll hear about this certainly on the news. These guys are much more flashy than us when it comes to getting teams of 30 people to the field and putting up lots of tents and bringing lots of equipment. We're much more lightweight. And hopefully bringing back some sediment. So here's some of the sediment that Gavin's brought back from the Cam Ice Stream. We're hoping that in Discovery Deep that we'll be able to drill down 200 meters into the subsurface and core some of these layers to understand what they are better. All right, so that's basically the science part. Just a couple of slides to think about the future. And I'm pretty hopeful for geology and for geology at Otago as we go into the future. We know that things like solar panels, wind turbines, batteries, even the things that are in your smartphone take raw materials, and geology and geophysics play a really big role in trying to find that, and a bigger role. And I think one of our messages in our department that we're trying to get out, especially to younger kids, is that there are careers here that you can help the world get through the problems that perhaps have been caused a little bit by geology, by trying to get carbon into the atmosphere. But our solutions also are going to require a lot more geologists who are really smart and are able to find these sort of things. And for example, last year, we had at least 5 of our bachelor students who went off to Australia to work in exploration for rare earth elements, which are required for all of these things. And just a little plug for the conference that's coming up at the end of this year. So Mountains to Sea, which will be here at the end of November. And one of the sessions, which is being chaired by a former PhD student of mine, Jess Hillman, is future-proofing energy and minerals, geosciences in a low-emission era. So it's certainly a topical subject. Also, I think something into the future is still going to happen as well. I don't know if people have seen maps like this before, but this is just a sample of some of the seismic data that's been collected off the coast of Otago and Southland over the last 10 or 15 years by industry, all paid for not by the government, but the government was very wily and smart and made sure that ownership remained with New Zealand. So we have access to all of this data, including some beautiful 3D seismic surveys, which I haven't shown you here. And this has been used as recently as last year by one of my master's students, Holly Meyer, who's looking at this oil industry data really for climate science purposes. So she's looking at the upper part of the sediment, trying to see the record of change that's happened through the last few glacial periods, seeing big canyons that have been incised and refilled several times over time. So it's been quite exciting to go back and use all this free data for pretty interesting topics. And also this whole topic of near-surface geophysics, near-surface seismic in particular, is something that we're getting more into. It has lots of applications for earthquake science. This was taken earlier this year with Maya, one of my 302 students, and I know Mark has an ongoing project here. And the Dunstan Fault will be going back to this location in the near future. We have our weight drop thumper, which the people in the field school will soon be playing with as well. So it's there's lots of amazing things I think that are still around for the future as we go. All right, and hey tangata, hey tangata, hey tangata. It's all about the people. My wife promised me that I wouldn't have a lot of thank yous, so I'm just going to show pictures instead, and of people, teachers and mentors of mine who've paved the way for me from right from the early days with family and coaches and teachers, PhD supervisors and postdoc supervisors and Alan and Richard, who are real help for me coming here. Then all my colleagues as well. That I work with really closely now. Some of these people you'll know really well. There's lots of others who have worked with me very closely over the years. And I had to have 2 pages of colleagues because there's lots of people I work with, and everybody who I've worked with in the department here is one of the best things that has really been helpful in my career has been being able to find all sorts of interesting projects of people, right, from paleontology to paleomagnetics and structural geology and climate science, whatever's out there. It's been really fun to work with you all. And I guess, and collaborators beyond the university as well. It's been great being involved in a lot of international projects and some local projects as well. The meetings I go to, it's always great to get together with people that are thinking about the same problems as me. And students. I really couldn't do this without my students. As Richard was saying, almost all my papers have students as my co-authors, and it's been a real privilege to work with so many amazing people over the years. And I'm sure that went in there too fast, but I'm sure you'll recognize some of yourselves, those of you who are here. And then finally, my whānau, I've got Sandy. Thank you very much. Thanks, Sandy, for all the advertising for today as well. And Claire, Connor, and Maggie, and the dogs. This is a big part of my support, but also my parents who are probably watching, and the more extended whānau that you know who you are here in New Zealand and around the world. It's been really great. So thank you. Into the sunset.
So my name's Mark Sterling. I'm the Professor of Earthquake Science over at the Geology Department, and it's my job to thank Andrew and say a few other things. So thank you so much, Andrew, for a really great presentation. Normally the thank yous would be done by the head of department, but it happens to be the head of department giving the IPL. But it's a real honour to have this position and be able to thank you. Before I give you a gift, a showing of our appreciation, I just wanted to say that a few nice things. Basically, Andrew's become head of department in the last few years, and it's been an absolute joy to have Andrew as head of department. We've had some really nice heads of department, and but Andrew, I must say, and echoing Richard's comments, he's the man of eternal optimism. He's always smiling no matter what's going on. And he has kept our spirits up. We've had some pretty challenging times in the geology department in the last couple of years. But Andrew's been there for us and always looking on the bright side of life. But in terms of Andrew's research, something resonates with me that he has gone from the industry, geophysics working for Chevron, into academia, and he's been able to transfer those skills and become highly successful as we see today, and that speaks volumes to me. So accolades to you, Andrew, for that. Also, as I say, what you've done for us in the department. So without further ado, I'm going to now present you with a gift, but before I do, you are all welcome to the staff club for refreshments after this, and I also should thank you everyone for coming, both physically and online. And Sandy, Maggie, Claire, Connor, in the abyss of the virtual world, Andrew's extended family. So thank you very much, everyone, and hope you will come to the top floor of the staff club and enjoy more celebrations for this outstanding professor here. So, Andrew, I'm going to give you a gift now.